Okay, so question number one, identify all points of equilibrium for this particle. Well, the important thing here is that when you look at a graph of potential energy versus position, the force is related to the slope. The force is actually equal to negative du dx. In other words, the force is equal to the negative slope of this graph. And the word equilibrium, by definition, means where the net force is equal to zero. So we're looking for locations where the force is equal to zero. We're looking for locations where the slope is equal to zero. So that's how you answer that question. So there's one spot right there at x equals 2. And here's another spot right here at x equals 5. So that's the answer to that question. Now, part B. The particle has a constant total energy of 4 joules. I find it helpful, and they have that drawn. I'll highlight it. That's the total energy of this object. Determine the kinetic energy of the particle at the following positions. The key to solving a question like that is to recognize that total energy is made up of potential energy plus kinetic energy. So the total energy is always 4. The potential energy can be read from the graph. At x equals 2 meters, according to the graph, the potential energy is equal to 1 joule. And so the kinetic energy is what's left over. And so the kinetic energy would be equal to 3 joules in answer to that question. At x equals 4 meters, reading the graph, the potential energy is equal to 3. So E equals U plus K. 4 is the total energy. The potential energy at 4 meters is equal to 3. And so the leftover is kinetic energy, and that's equal to 1 joule. Can the particle reach the position x equals 0.5 meters? X equals 0.5 meters is here. And if you go up and look at the graph, that corresponds to that much potential energy, which looks to be about 5.5 joules of potential energy. So the answer is no. The total amount of energy that this particular particle has is 4 joules. And so it's impossible for it to be in a location where it would need 5.5 joules to be at that location. The second part of the question at x equals 5, that would work because the potential energy needed to be at that location is less by just a little bit than the 4 joules of total energy that this object has. Final question is to create a graph of force versus position. And this goes back to, give me a moment here, I'm going to clear some things. This goes back to what I was saying earlier, and that is that force is the negative slope of the potential energy versus position graph. So what I would do is take some points and calculate some slopes. And there's a degree of approximateness here, admittedly. So this point here is 0,8. This point here is 1.5, 2. Find the slope, which is y2 minus y1 over x2 minus x1. And so the slope here is -6 over 1.5. And let me grab my calculator. I should probably be able to do this in my head. It's 4, right? No, it's 9. Okay, anyway. Is that right? 6 divided by 1.5. Yes, it's 4. Okay. So the answer there is -4. The slope is -4, but remember, force is the negative of the slope. And so the slope here is negative, or the force is -4. The force is 4 newtons. So from position 0 to position 1.5, the force is 4 newtons. So I'm going to recreate that down here. Here's position 0, here's position 1.5, there's 4 newtons. So that's what the force looks like during that section. Now, let me take another slope. This point here is 2, 1, and this point here is 4, 3. You might wonder, why am I picking those points? I'm just trying to pick 2 points that are obvious to me and definitely part of a straight line. So finding the slope there, y2 minus y1 over x2 minus x1. 3 minus 1 is 2, 4 minus 2 is 2. That gives me 1. Then, of course, the force is the negative of that. The force force would be -1 Newton. So that's from 2 to 4. And then lastly, let me get the slope of this section right here. Again, just picking 2 points that look like they're relatively easy to use. This looks like it's about 5.6, comma 3, and this would be 7, comma 0. So 0 minus 3 over 7 minus 5.6. And that is equal to 3 divided by 1.4. That's equal to 2.14. And so that means the force is the negative of that. I'm sorry, this was negative. Force is the negative of that, so the force is positive. So we're back up at about this moment right here to 2.14, somewhere around there. Now, you'll notice I haven't connected these points, and let me read the exact directions here. It says, carefully draw a graph. All right, so I guess we have to be careful about drawing this graph. But I would, there's a transition zone. There's a curved transition zone in here and in here. And so I would just sort of smoothly, as best as possible, try to connect these zones. And I think that would be acceptable.